students, chapter 11, thermal properties of matter. Today in this topic we will see one important topic, that is heat transfer. Heat transfer, that is exchange of heat. Okay, yes, heat transfer means energy transfers. Heat is flowing from one point to another point, means energy is flowing from one point to another point. So first of all we will see the modes of heat transfer. Yes, modes of heat transfer. There are three modes of heat transfer. First is conduction. Second is convection, and third one is radiation, and third one is radiation. Okay, so there are three modes of heat transfer: conduction, convection and radiation. Okay, now we will see in detail, okay, what is meaning of conduction, what is meaning of convection and radiation. So first topic that in this chapter we will in this lecture we will cover is, yes, conduction. Is conduction. Okay, what is example of conduction? It is very simple example. Suppose you are given one thin rod like this, one thin rod like this, a metal rod. Okay, and here if it is burner, it supplies heat energy. It supplies heat. Then what happens? Yes, we know that heat is transferred in this direction. Yes, heat is transferred in this direction. Yes, heat is flowing from this end to this end. So yes, after some time you cannot hold this rod in your hand. Okay, yes, okay. So this mode of heat transfer is called conduction. In conduction, what happens actually? See, here it is. In this rod, there are numbers of particles, constituent particles. Numbers of constituent particles. Okay, so what happens? If yes, you are giving heat only to this end, then how it is transferred towards another end? Okay, so if you are giving heat to this end, means these particles, by absorbing heat energy, their temperature increases. Okay, by absorbing energy. Okay, their temperature increases, their energy increases. Yes, the temperature increases, their energy increases, and due to that, their thermal oscillations increases. Yes, the thermal oscillations increases, and this particle will transmit its energy to this nearby. Because see, if its thermal oscillations increases, it disturbs the second particle. Means we can say the energy is transferred to second particle. Now again, second particle, temperature increases, energy increases, its thermal energy increases. So yes, it will disturb its next particle, next particle, next particle, next particle. So in such a manner, the heat is flowing from one end towards another end. From one end towards another end. And yes, what is reason? What is reason for flow of such heat? Temperature difference. Yes, temperature difference. Okay, here due to temperature difference, heat flows from part of higher temperature to part of lower temperature. Clear? Yes. Heat flows in conduction from higher temperature to lower temperature, from higher temperature to lower temperature. Means due to temperature difference, this conduction takes place. Okay, due to temperature difference, conduction takes place. Okay, clear? Not any particle will move from one end to another end. Okay, there is no actual motion of particles. Okay, in conduction there is no actual motion of particle from one part to another part, from one part to another part, it just transmits its energy. 1 to 2, 2 to 3, 3 to 4, 4 to 5, etc., etc., etc. This particle will not move towards this hand. Clear? It will not move. It will not. Clear? So this point you have to remember in conduction. Yes, this one. Okay, no actual motion of particle from one part to another part. It just transmits its energy. Okay. So yes, it is theoretical thinking about what is conduction. Okay. And yes, you know examples of conduction. Okay, if you give heat at this one end, then after some time heat is transferred towards the second end. That is simple conduction. If you place on a vessel on gas burner, okay, and if it is not insulated, then after some time, if you touch that vessel, you will feel, yes, it is at high temperature, it is hot. Okay. Now we will see equation. Okay, yes, this conduction, in conduction, this heat flow, it is due to heat transfer, it is due to temperature difference. So on what quantities this heat transfer depends. So see, if you have conductor like this, if you have any conductor like this, which is maintained at two temperature, here it is T1 and here it is T2. These two temperatures are maintained constant, okay, actually. So T1 temperature and T2, and yes, here I am giving one condition. Here T1 is greater than T2. T1 is greater than T2, means it is at higher temperature. This side it is higher temperature and this side it is lower temperature. This side it is lower temperature. Okay, so heat flowing, heat, okay, heat I will represent by X. Heat flowing in this conductor depends on which factors. So I will write here, okay, heat transfer depends. Heat transfer depends, or you can say, okay, that transfer of heat current, you can say heat current or rate of heat flowing, etc., etc., etc. So the rate of flow of heat transfer rate is directly proportional to, I will write heat transfer rate, that is H. That H is directly proportional to temperature difference, delta T. That is temperature difference. Second, H is proportional to A. What is A? A is cross-sectional area. What is A? Cross-sectional area of this conductor. Okay. So yes, heat transfer rate or rate of heat transfer, H is proportional to delta T, that is temperature difference. H is proportional to A and H is inversely proportional to its length. H is inversely proportional to its length. So if it is length L, this cross-sectional area, this cross-sectional area is A, then this heat transfer rate, H is directly proportional to delta T, H is proportional to A, and H is proportional to 1 upon L. If you combine all these conditions, then yes, you can write the rate of heat transfer. Rate of heat transfer, H is proportional to, it is A delta T upon L. If you remove proportionality, then you have to add some constant. that is H is equal to Ka delta T upon L. And yes, we can also write this equation as Ka delta T, which is T1 minus T2 upon L. T1 minus T2 upon L. Where? What is K? Where K is constant of proportionality and it is called thermal conductivity. It is called thermal conductivity. Clear? So yes, this equation you have to remember. H is equal to it is Ka T1 minus T2 upon L. H, you can also write this H as, see, H is equal to, you can write dQ upon dt. That is rate of heat transfer. Rate of heat transfer. Rate of heat transfer is equal to, it is Ka T1 minus T2 upon L. T1 minus T2 upon L. Okay. So yes, where what is each and everything actually? H you can say heat current also. H you can say heat current. dQ that is heat energy. dQ that is heat energy. dt that is time. K that is thermal conductivity. A that is cross sectional area. Okay. A that is cross sectional area and L that is time. Now from this equation, if you make K as subject, then make K as subject, then K is equal to it is dQ L upon dQ L upon dt A T1 minus T. T1 minus T2. You have to make K as subject. Then how to obtain this unit? So how to obtain this unit? Unit of K. Unit of K is equal to dQ, its energy, means it's joule. L that is length, means meter. dt that is time, means second. A area means meter square. And it is temperature difference, means Kelvin. So 1 meter cut, 1 meter cut. So is equal to it is joule, second inverse, meter inverse, Kelvin inverse. Or joule per second, energy per unit time, it is called power, means watt. So is equal to it is watt, meter inverse, Kelvin inverse. Clear? So yes, you have to remember what is rate of K, that is thermal conductivity. Okay, it is joule per second per meter per Kelvin or watt meter inverse Kelvin inverse. Clear? Yes. So it is one equation that you have to remember. Now see, H is equal to Ka T1 minus T2 upon L. I can write this equation as H is equal to T1 minus T2 upon L divided by Ka. Yes, I can write this Ka in denominator of denominator. Then see, what is H? Again, I will write it. Okay, H is heat current. H is heat current. T1 minus T2, temperature difference. Yes or no? Yes. L upon K I will write as this. Okay. Now I will write one equation that you already know. I is equal to V upon R. Yes. I is equal to V upon R. I is equal to V upon R. So what is equation? I is equal to V upon R. See, here it is. I is called electric current. I is called electric current. What is V? V is called potential difference. V is called potential difference. And what is meaning of R? R means electrical resistance. It is electric resistance. Yes, you know condition for flow of electric current. Electric current is flowing due to potential difference. Electric current is flowing due to potential difference. Similarly, heat current is due to temperature difference. Heat current is due to temperature difference. So if we can compare this two equation, this R is electrical resistance, then if it is heat current, it is due to temperature difference, then this L upon Ka represents thermal resistance. Yes, L upon Ka is called thermal resistance. Here L upon Ka is equal to RH, called thermal resistance. Yes, it is called thermal resistance of conductor. Clear? So this point you have to remember. Equations, again, this equation you have to remember based on this equation. H is equal to dq upon dt is equal to Ka T1 minus T2 upon L, and second equation is of thermal resistance, that is RH is equal to L upon Ka, where L is length of conductor, K thermal conductivity of given object. See, thermal conductivity depends on material. For different objects, for different material, thermal conductivity is also different. Yes, thermal conductivity is also different. And A, that is cross-sectional area. Yes, A is cross-sectional area. Clear? So yes, it is about what is heat transfer, modes of heat transfer. From this mode of heat transfer, one thing, that is what is conduction. For conduction, what is equation? Okay, now next. Okay, now one more important thing about conduction. So suppose it is conductor. At this time temperature is T1, at this temperature is T2, and heat is flowing in this direction, that is H. So obviously it is hot end and it is cold end, because heat transfer takes place from temperature, higher temperature to lower temperature. You can remember like this. Okay. One important quantity, that is temperature gradient. Temperature gradient, it is denoted by dt upon dx, and its equation is it is minus T2 minus T1 upon L, or you can simply write as T1 minus T2 upon L. Okay, but why here minus term is? Okay, so what happens here? As you are moving from higher temperature towards lower temperature, temperature decreases. For example, it is 100 degrees Celsius, it is 90, it is 80 degrees Celsius, it is 70 degrees Celsius. So as you are moving from hotter end towards colder end, temperature decreases, distance increases. Temperature increases, distance, temperature decreases, distance increases. Okay, so as you are moving from hotter end towards colder end, what happens? So yes, temperature decreases as it increases. So temperature gradient, its answer will become negative. Okay, if I give you some example. Okay, for example, it is one like this. This end, its temperature is 100 degrees Celsius. This temperature is 50 degrees Celsius. And length of this, it is 100, not 100, it is 25 centimeter. Then for this rod, what is temperature gradient? So dt upon dx is equal to how to write this? So yes, it is T1 minus T2, means it is 100 degrees Celsius minus 50 degrees Celsius divided by 25. So 100 minus 50, it is obviously 50 divided by 25, so it is 2. But what is unit? 2 degrees Celsius per unit, it is in centimeter, per centimeter. So meaning of this, if we move 1 centimeter, temperature decreases. If we move 1 centimeter, temperature decreases by 2 degrees Celsius. So from here at 1 centimeter, what will be temperature? Temperature will be 2 minus, means here it will be 98 degrees Celsius. Okay. If we are moving 2 centimeter, then temperature decreases by 4 degrees Celsius. Then from the same rod, if here is 100 degrees Celsius, then at distance 2 centimeter, what will be temperature? Yes, temperature decreases by 4 degrees Celsius, means temperature will be 100 minus 4, means 96 degrees Celsius. So it is meaning of temperature gradient. Yes, it is meaning of temperature gradient. Clear about this? Okay. Yes. You do not have to write this formula. It's okay. Yes, you have to remember this meaning of this. Now, we know that when electrical resistance they are connected in series, that is R1 and R2, then equivalent resistance is RS is equal to R1 plus R2 for series connection. For parallel connection, if it is R1, it is R2 in parallel connection, then what is equivalent resistance? Yes, 1 upon Rp is equal to 1 upon R1 plus 1 upon R. Similarly, when you are given combinations of some conductors means like this. Okay, if you are given one conductor like this, it is one conductor and it is another conductor. Okay, and it is temperature difference, that is here it is T1 and here it is T2. So heat is transferred from in this direction. Here T1 is greater than T2. So it is called series connection, and in such series connection, if resistance of this is RH1, resistance of this is RH2, resistance of this is RH1 and resistance of this is RH2, then what is total resistance RH? It is RH1 plus RH2 in series connection. In case of parallel connection, okay, if you are given two slabs like this, one like this and another like this, this having resistance RH1, this having resistance RH2, and here it is T1 temperature, here it is T2. So they are said to be in parallel connection because two different mediums. Okay, so it will flow like this. Okay, so in this case, what is equation of resistance? Yes, equation of resistance is 1 upon RH is equal to 1 upon RH1 plus 1 upon RH2. Okay, so in case of connections for conductors like this, okay, if they are given in series connection or if they are given in parallel connection, then you can write equations of resistors like this. Clear? The concept of this temperature gradient is not given in your textbook. Actually, it was given in old textbook. Okay, with some modification. So here you have to understand what is meaning of temperature gradient. There is series and parallel connection. Okay. One thing, thermal steady state. What is meaning of thermal steady state? Thermal steady state. If you are given here one conductor is under thermal steady state, so meaning of that thermal steady state is yes, is it visible? Yes, it is visible. So meaning of thermal steady state is, okay, for that given conductor, okay, dq upon dt, that is rate of heat transfer, and dt upon dx, that is temperature gradient, they both remains constant. So this one point you have to remember. Temperature gradient, from this equation it is clear, it is dt upon dx. So its unit is, what is unit of temperature gradient? Its unit is dt, means it is Kelvin per meter, or you can say degrees Celsius per meter. Clear? So yes, it is about what is temperature gradient, series and parallel connections for conductors, thermal steady state. Okay, so yes, this is it for today. Now in next lecture we will see what is convection and what is radiation.